Hello everyone. Today we will discuss about phasors. We represent the voltage and current in the form of rotating vectors called phasors. Why do we represent it? What do the different parts of the phasor diagram represent what quantity when we are talking about rotating vectors, when we are talking about voltage and current representation of AC in the form of phasors. That's all. That's what we are going to discuss in the present video. So what are phasors? Phasors are the rotating vectors which rotate about the origin with the angular frequency omega. So these are the rotating vectors which rotate about the origin with an angular frequency omega. Its length gives the magnitude of the quantity, the maximum value or the peak value of the quantity. So we'll just mention it. Right? So it's moving with angular frequency omega. So then if this is the time elapsed, then this angle will be omega t, right? Now the magnitude of this rotating vector gives the maximum value or the peak value of the quantity. Now here we are using phasors to represent the current and voltage. Why are we using it? We know that the current and voltage are scalar quantities. Even then we are using it. We know that AC current and AC voltage are sinusoidally varying quantities. And this can be compared with the harmonically varying quantities. We know that the equation of simple harmonic motion is A sin omega t, which we have studied in class 11th. So here this is, the voltage is represented by this, so sinusoidally varying quantity, and current here is also represented in the form of sinusoidally varying quantity. So I have taken a particular case just to give an example that both are sinusoidally varying quantities. Now here it is observed that the sinusoidally varying scalar quantities give the same results as given by the phasors, which are vectors. So we are using the phasors to represent these quantities. As we know, the rules of adding phasors. So we know that these are sinusoidally varying scalar quantities. Now these are represented in the form of phasors because these additions give the same result as given by the phasors, which are actually rotating vectors. So for the simplicity in solving such problems, we are using phasors because we know the rules to add phasors or vectors. So we are using already known rules to solve the complex situations of the sinusoidally varying voltage and current cases. So we can represent this current and voltage here, and I'll show you how to represent the peak value of the current and voltage in such case. Suppose you have this voltage which is represented by this. So this magnitude will give you the peak value of this voltage, and its projection here. If time t is equal to 0 here, then this theta angle will be omega t, because we know that omega is equal to theta upon t. It's rotating this way, so we can find its projection here using trigonometry as we had done it in class 11th. So this is also omega t, and this value, the magnitude of this vector is actually E naught, which is this length. So using trigonometry, you can write a relation between this and this. So this value comes out to be E naught sine omega t, right? So this gives you the value of the voltage at a particular instant t. We have found the projection by dropping a perpendicular from the ends. One perpendicular is here and this end is already here. If you remember in class 11th, I told you the way of finding the projection. If you have an arc MN and its projection will be found by dropping a perpendicular on the given line. So this is AB. So the length of this, the separation between the foot of these perpendiculars gives the projection. So you can write down here that AB is the projection of MN on L. So here we are finding the projection of this vector. So I'll drop a perpendicular here and a perpendicular here. So this length will give you the projection of E naught on vertical line here. Now if I have current also here, suppose the current is here, it will be messed up. I'll draw it in the I would like to draw it in a separate diagram. So if I want to draw it for current, then if this is your current, this is omega t, then the projection will be this, and this will give you I naught sine omega t, and this will be the value at any instant t, right? So this way we are representing the voltage and the current in the form of rotating vectors, because their projections give the same results as we get in the case of phasors, because this is also a harmonically varying quantity, as we had discussed the harmonically varying quantities in chapter 14. So I hope the basic concept of phasors is clear. You have got this projection as the value of EMF or current at a particular time t. So this is the projection actually. So this was the basic concept which was required to be given here. And why is this required in this case? Because in case of inductor and capacitor, which we will discuss, the voltage and current are not in same phase. In the case of resistor, these are in same phase, so these can be added as it is. But in case of voltage and current phase difference, which is different in inductor and capacitor, we need this quantity to represent these. So that's all for now. Have a nice day.